This is week 4, lecture 2, and I'm going to be starting the subject of analysis of an assembly today. Although assemblies can be applied to a situation where all three types of elements are involved, but for the next three lectures, I will concentrate only on solid elements. Later on in the first part of the course, I'm going to come back and do problems where all three types of elements may be present, and you may want to do it as an assembly problem. But here's the situation. This is the agenda for today. I'm going to solve this problem uh, both with and without planes of symmetry, all planes of symmetry. Now remember, on the test, on the midterm, you will be asked to use all planes of symmetry that are applicable, if any, and obviously the most appropriate element. But first, I'm going to solve this problem without any planes of symmetry, and then come back and repeat it with planes of symmetry that are applicable to the problem. Here's the situation. We have a block, steel block, given on the left side with the dimensions given. And there are two pins which are identical, and they're inserted symmetrically into this block. Okay. Now the two ends of the bottom pin, the faces of the bottom pin, are clamped, and somehow the two faces of the top pin are pushed up or pulled up by 0.01 inch. Of course, you want to solve the analysis, solve the problem, and then find the stress distribution and everything in it. But we also want to find out how much force is needed if you could actually do this. Okay. Now, before we do any problem, notice that because of the way the geometry is or the assembly is, and because of the way the restraints and the loads are, definitely X, Z is a plane of symmetry, and YZ is also plane of symmetry. Okay, XZ and YZ are two planes of symmetry. But keep in mind that XY is not a plane of symmetry, because what you're doing on the top to the pins and what you're doing to the bottom to the pin are different. What you're doing to the top to this pin, on the top pin, is pulling it up, and what you're doing at the bottom pin is clamping these. So XY is not a plane of symmetry. When I come back, I will do this with plane of symmetry, cutting it with the XZ and YZ plane. Okay, but for now, no planes of symmetry. So you are automatically in the product file. We always close this thing because we never had an assembly, or I never had an assembly for you. Now we're going to analyze assembly, so we keep this thing, and then I save this thing, file, save management, save as, on the desktop, on my desktop. Desktop. I'll make a new folder, and I will call this thing my assembly no planes of symmetry, no planes of symmetry. And then everything is going to go in there. So that's the product. Let me make the block first. So I go insert a new part in there, and I'm going to call this thing the block. Right click properties. I'm going to call this thing block. This is the instance name, and there's the part name. Continue does not have part name, it calls it product. Sorry, part number. Okay, let's go make it. So go to the part design, and this is not part design. This is the wireframe and surface design. So I'm going to switch because I want to make three-dimensional object. I'll go to part design. On that vertical plane, I will sketch a symmetric shape, because later on I'm going to cut this thing. I might as well do my job easier right now. So I'm going to draw a symmetric rectangle like that. and we're going to dimension it accordingly. So for example, I'm going to dimension this to be 10. And if you look at the drawing or the slide, this is going to be 4 inches. 4. I accidentally closed the window here. I don't know what toolbar here. I don't know what it was, but so we'll get it when we need it. Okay, so I need a circle up there, which is 1 inch away from the top. Oh, it's the dimensions, yeah. So it was constraints. I close the constraints. So view, toolbar, constraints. Where's the constraints? I think it was, actually, maybe right there. Okay. So let's look at this thing from the normal view so that you get disoriented. This is going to be 1. Diameter 1, I believe. All right. And I'm going to mirror this thing down here. So mirror, get the mirror icon. Or draw another circle. That's up to you. There. Exit. And pad it in each direction by 0.5 to get the total thickness of 1. So I'm going to do mirror extend 0.5. Good. All the way on the top. Insert a new part. Read this thing carefully, please. I say no. In other words, I want to use the same origin as the assembly origin to do all these parts, basically. So right click, properties. I'm going to call this thing top pin. Top pin. And the part name or part number is top pin. Okay, make it. Double clicking on top pin. All right. Now, on this plane, on that vertical plane, I will sketch. Why don't I project that circle? Because it has the same diameter as the hole. So find the project. This project is very important. We're going to do that a lot. Project. I select that circle. Notice that it is projected. Not the whole face, actually. Control Z. That's not what I wanted. I just wanted the circle. That's all. So project just a circle. Just a circle. There. I don't want the whole thing. There. Now exit, and the length of the pin is 3. So I'm going to pad this thing. Mirror extend 1.5 in each direction. 1.5 in each direction. Good. All the way to the top. And this bottom pin is exactly like the top pin. It's crazy. If I do it again, I can do a copy paste, or I can use instances, but at least for this video, I'll do crazy thing. I'll say insert a new part. I say use the old the assembly origin for it. Right click, properties. I'll call it bottom pin. This is crazy because they're identical. You should not waste resources like this, but that's fine. Or you can do instantiation if you know what I mean. Otherwise, just go make it. Double click on it. On that vertical plane once again. Select or sketch. Project the bottom circle. Good. Exit. Add it. Mirror extend by 1.5. Please make sure you keep up with the course content. All the way to the top. This is not getting any easier. It's not getting harder either, but you have to keep pace with me. Now, because everything is made out of steel, what I can do is that I can apply it to the product, and every one of them is going to be the same same material. So let's find the material, the apply material here. It's made out of steel, metal, steel, and if I apply it to the product, it's going to put it on every single part. Good. So let's click on the floppy so that this product is saved in that folder. Remember, I initially saved it, and then from now on is, I should have called this thing bottom pin, but that's okay. Anyway, so now we are pretty much done here. And I'm going to go to analysis and simulation, generative structure analysis. CATIA says, okay, static, yes, static. And notice that CATIA sees three solid parts, the block, top pin, and the bottom pin. And immediately it measures that. You can see that right there. This is for the top pin, this is for the block, and this is for the bottom pin. Another way that you can see that is in the tree. Now, if you want, you can say right-click mesh visualization and look at it. And notice that here, the reason that these were selected to be different, the reason that they were selected to be different sizes is that CATIA looks at the size of the object, and based on that, it comes with a default with the default value. Okay, this was bigger, so it uses a bigger element. I'm going to make everything parabolic, by the way. It is parabolic. Good. And remember, you may want to do local mesh refinement around the hole. You should be able to do these exactly like we did before. Okay, so first of all, deactivate that. I'm not going to do that today. Okay, deactivate that. Now, the properties are automatically done because CATIA did it for you. So let's clamp these edges. So we say clamp this edge. Oh, this edge, not edge, the face and this face, because we were told that the bottom pin has clamped faces. And this is being pushed up. Remember how to push up. First, you make it 0 value. So this displacement in the direction Z of this face and this face. And remember, it's not user, global, because last time that I did this thing, it was user, so it stays there, unfortunately. So here, this face and that face is first pushed by 0 amount, and now I can apply enforced displacement, and you select it either from tree or from the screen, and it's this. This is the pushing up by 0.0, I don't know, that problem is 0.1 inch. Problem statement, whatever it happens to be. Good, good. So save the analysis. Very important. File, save management. Here's the analysis file. Save as. You have a folder called assembly, my assembly, no planes of symmetry, okay. Analysis, and say okay. And right now, in that folder, there are 4 files. There's a product, there's a top pin, bottom pin, block, and analysis. Let's check that. Let's check that. I don't need this. What is it called? My assembly, no planes of symmetry, 4 files. Product, block, top pin, bottom pin, analysis. And remember, on the exam, if there is an assembly problem, you have to give me all of these. The product, all the parts that make it, and the analysis. Let's go back. Now, you may get the impression that things will work fine. So let's go ahead and run it and see what happens. And it will bomb out for a reason that you'll see in just a minute. And there we are. It says, I can't run it. Do you see what the issue is? If you don't, maybe CATIA will help you. Let's plot the deformation. Deformation is this level right there. And animate it. What it's saying is that, look, these parts don't see each other. That block does not know that there's a pin in it and stays in it. So this is why when you do analysis, you're multiple parts and you have to tell the software how these multiple parts interact with each other. So let's start with our first one. Cancel that. Look, look. This pin is actually cutting through that because it doesn't know that there is a block coming towards it. Close that, deactivate this, and we do the rest of the problem. Deactivate. Good, good. Now, anything that you don't want to see, you can just hide. For example, all these restraints, I don't want to see. Let me hide them. All the loads, I don't want to see. Hide them. Okay. And these guys, if you don't want to see, just hide them. Can I do it like that? Yeah, good, good. So, when it comes to interaction or connections or parts interacting with each other, this is the thing that you need. It's called analysis support. So you click on the first one, general one. It says, okay, you know that there are two things that eventually will interact with each other. So what are they? Well, this plane, the surface of this, the surface of that pin, first component. For the second component, the surface of the hole. So let me right click here, hide it, and select the surface of the hole. And if you want, I can call this thing, I can call it instead of one, I'll call it top pin block. Terrible way of writing the name. Top pin block. Good. All right, we did one. So notice that a connection has been created here. Top pin block. I do another one because this pin also does not see that block. So I need another one. I'll call this thing bottom pin block. What did I call this thing? Bottom pin block. Okay, and then for the components, select the surface of this, or actually put the cursor there so the surface is selected, and then hide it, right click hide. For the second component, select that surface. You say okay. Notice that these are created. Okay, it says, all right, I know that these guys are related to each other. The question is how? So the how part is right here. Let me move this thing so you can see it better. Connection properties. So this is to establish the connection and then properties. Right now, today, I'm going to do the first set of toolbars. Can I put it up there so you can see it better? Face connection. I'll put it up here so you can see it better. And if you scroll through it, one of them says contact. So slider, don't worry about that, contact. That means the pin and the hole are in contact with each other. They can penetrate each other. You click on it. It says, what's the first one? This top one is contact connection. Don't worry about these buttons right now. Do another one. Second one. And notice that the icon for contact is two things as if they're contacting each other. Okay. Those pins are in hiding. So let me bring it in the front so that you don't get confused. These pins are, you can do it from here or the tree, whatever is more convenient for you. Okay. So now, first of all, save it and then run it and see bombs out again. Okay, bombed out. Can you tell me what the issue is? Well, we had the deformation here. Let me activate that and let me animate it. Remember, change the scale first. Where is the scale here? Change the scale to default. Okay, good. And run it or animate it. You see what happens. The pin does not penetrate the block, but it can slide out. So as a rigid body, when you think about it, this block can, because there's no friction here, we didn't do anything about friction, this block can actually slide out, or the pin can slide out. So we have to take away that rigid body motion. And I say close, deactivate that, deactivate it. Okay. So the different ways of handling this thing, one of them is this bottom one cannot slide out because these were clamped. So what we can do, we can take one point or one basically surface, say, hey, you cannot come out. How do we do that? User define. I'm trying to find my restraints right there. This is why it may be a good idea to close the stuff that you don't want so that there's not a lot of garbage in front of you. And I don't want that. If you ever want it, you can always get it back. Hopefully you know how to get it back. But anyway, so I'll keep these things here. Now, user define, we can select a point here, okay, and say, hey, you can come out. So there, no motion in the Y direction, that face, select that. Yeah, say uh, no motion in the Y direction. So this guy cannot come out. And let's run it again. I hope that, oh, the loads are not showing. I hit the load, that's why I can't see them. And the restraint, sorry, the restraint, I hit them, so it's right there. Because I hit them, you cannot see the proper thing. Let me hide the load here. You can see that. It cannot come out. As a matter of fact, what I can do is instead of coming out, because this can also spin inside of that, so I can say, hey, you cannot, you see that? You cannot go in that direction. This one was pushing it up, and I say you cannot go in the direction X either, because otherwise this pin can spin in there. Okay? It can no longer spin. Say okay, and let's run it and see what happens. I don't have to do it to the other side because it really doesn't matter. It's just that they'll take care of it. Okay, so let me save it. And solve it. Okay, something is coming out. And it must be this block. You can see that. Let's see that. Let's, where's this guy? Yeah, deformation. Now the block is going to slide. The pin doesn't go anywhere. The block can slide. We say, fine, no problem. Deactivate that. Now go and select a single point at that corner, or this corner, or that corner, etc., and say, do not move in the direction Y. We say, okay, save it, and now run it. And now show me the deformation. Didn't give me an error message. That's good. Activate and reset the scale so that we can see what's going on. Here's the reset the scale. And there we are. Isn't that the way it's supposed to be? You see that? Something that's bothering. Yep, no, that's okay. That's okay. The only thing is that uh, what I should do is, because notice that this is sliding sideways, okay? Which is fine, except that if I don't want that, if these are symmetrically inserted, there are different ways you can fix it. For example, deactivate that and say, hey, you can't go in that direction either. So you can do it like that. So another one is this point. Don't go that way. And we say, okay. And now run it. And look at the deformation. That's the way it should be, right? Yep. Very good. Okay, now, you want to look at the stresses? No problem. Plot the von Mises stress. Change the rendering to material shading. Anything that you don't want, you hide. So, for example, these are states that I don't want to see. The load that I don't want to see. The connections that I don't want to see. Connections are all the way on the top. Okay. And the elements, these connections, yeah, I did hide them. Yeah, these things I don't want to see either. Maybe you have to do it from here. Oh, I'm sorry. Here, hide all of them. I can still see these guys. I can still see these guys, and I don't like it. Hide. Yeah, it's gone. Good, good. Anyway, now if you say, well, wait a minute, I'm not interested. You know what? I noticed something that on this side, if I don't apply that moving out thing, see that? It looks like so. So maybe what I should do, what I'm going to do is not maybe. What I'm going to do is I'm going to do the following. Uh, Let me go and deactivate this first. This is the one that I use to pushing up. This is the one that I use to prevent it from going sideways. So if I select both of them, this side and that side, I don't even need that very bottom point. Remember I fixed the bottom point here? Remember I fixed this bottom point? The reason I needed that is that because I didn't select both sides of this. Let me delete this. I don't need it. You see that everything's going to go look fine. Let me run it. It's going to be fine. It's going to be nice and symmetric. There's no doubt about it. So deactivate the one Mises stress. Look at the view from the front. Is that the front? Yep. You can see that last time I had to fix this bottom point because the block was going sideways. But because of what I did, exactly the same thing here that I did there, this is going to deflect symmetrically. I didn't want the block. I didn't need to fix the bottom point of the block. Just the top point would have been okay. So animate. Now, if you also want to see the stress distribution in the block, double click on it, select this, the selection, choose the selection, and say, just show me the block. Right there. Right there. And needless to say, all the stresses are at the top and the bottom where the pin is interacting. That there's very little stress everywhere else. Okay, now, how much force is needed to move this thing up by what we did? So here's what we're going to do. We're going to put the cursor there, right click, create a resultant sensor, create a reaction sensor. You remember that from the second week of the course, okay? And for the entity, we can either select it from, well, we have to, which one was the one that we pushed up right there? So this is the one that we use to select, to push it up. Remember? Push it up. This is to prevent spinning of the pin. This is to prevent the block. So that's why it would have been better if I actually named these things. But anyway, update. It says 23,000 pounds. That's a huge load. Again, I'm not looking at the validity of these numbers because you really have to be doing mesh conversion study. But if you trust this is how much force is needed, total force. So obviously you do half of it on this side, half of it on that side, right? Do not multiply this thing by 2, etc., because we're not using any symmetry at all. This is the total force. If you have to grab this thing, you have to grab it at both ends. You pull it up. Half of it on this side, half of it on that side. All right? So that takes care of this problem without planes of symmetry. Now I'm going to repeat this problem with planes of symmetry. Okay. So first of all, I'll go and click on the floppy so that my analysis is all fixed. Set. Now I have 20 minutes. I'm going to repeat this thing with planes of symmetry. Okay. But I'm too lazy to do it. So what I can do is the following. I'm going to go up here to File Save Management. If it's too much work, you go and do it from scratch. Okay? So I want all of these, okay, except for the results. I don't want the results. These temporary files I don't want. Okay. Let me do it like that. Take the product, save as, one level up. I make a folder called my assembly. My assembly with symmetry. Say okay. Save. Now say say propagate directory. So what it does, it will not touch the stuff that you have done before. It's taking this stuff and put it in a new folder. And that new folder was called My Assembly with Planar Symmetry, propagate directory, and then say OK. So I'm going to show you what happens. If you go to desktop, I have two, or I go to my desktop. There are two folders here. One of them, it says My Assembly without symmetry, no planes. And this is the stuff that you already did and the analysis, and you saved it here. No problem. I'm going to close that. If you look at this other folder, My Assembly with Symmetry, okay, there's no analysis because I didn't select the analysis. I select the product and said, hey, put it in another folder and what is that? Put it in another folder and uh, uh, do not basically link between the two folders without assembly and with assembly. Without symmetry and with symmetry. Look, if it's too much work, go make the part. The only thing you should not do is to right click and rename stuff. You should not do that. So I say, okay. All right. Let me close this. I don't need that. I don't need that. File, open in that new folder that I made for you, which was called, what was it called? My Assembly with Plane Symmetry. Select that product and you say, okay, there we are. Now we start cutting it. Cuts here will not affect the other folder. And we're going to check that. So for example, go to the block, double click on it, and you can split it. You can split it with, for example, XZ plot or YZ plot. The alternative, go up there. There is a saw here. See, there's a saw here. Let me get the saw for you. Must be right there. This saw will cut everything in that assembly. So let's see, bottom left corner says select a plane face, or a surface. So I'm going to select this, and it says, hey, all of these are going to be affected by this. Are you sure? The answer is yes. I want all of them. Doesn't matter what side we pick, right there. Another saw, another split. Select this plane. It says, hey, these parts are going to be affected. You want them all? Yep. Doesn't matter what side? No. Now, let me save this thing. And to convince you that the other fellow is not affected, let me go to File, Open, one level up, and my assembly, no planes of symmetry. Double click on it, select the product. This one, the parts must be exactly like they were. Let me do the following. Let me close this. Okay. Let me try it now. File, Open, no planes, product. There we are. This is what it was before in the original folder. Let me close that. File, Open, one level up, with planes. And say product. Say, okay, this must be the one with the cuts. There we are. Too much work? Do it your way. I don't care. All right, so now we're going to go to analysis and simulation, generative structure analysis. CATIA sees three elements or three blocks or three solid pieces. It meshes them automatically. Good. The rest of the problem is the same. First of all, let's take the stuff that is on the surface slider. Select this. Anything that you cut, that circle, turn it around, that guy, and this piece, and by the way, this piece down here, and this piece, and that piece, these are because of symmetry, okay? Now, I want to clamp that end, clamp this, say okay, all right, and then we want to move this thing up, so we first move it up by 0, zoom in, by 0 amount, and once you did that, then you're going to say enforce displacement of that restraint by 0.01. We will not have the problem of this pin sliding out because there's a surface slider here. We will not have the problem with the block sliding out because there's a slider surface here. Okay, let's save our analysis. File, save management. Here is the analysis. Save as in the proper folder. That is your proper folder by assembly with symmetry. You say okay, and now run it. No problem. Okay, this is the usual message that you get for, oh, connection. Of course, we forgot the connections. So we can see that the connections were not created. That's why one cuts through the other one like a knife through the butter. So that's the whole problem with assemblies. You have to create connections. We do exactly the same thing. First one, for example, this face to this surface. Second component, hide that guy, that fellow. Do another one. Notice that the connections are created. It's a good idea to name these things properly so that you can identify later. Another connection. This face. Order is not important. You can select the order of you can select the hole first. It doesn't matter. So the connections have been created, and both of these are contact. Once you create a connection, it means that you say they're somehow related. You have to say how they're related. So we go to this toolbar. Remember that the connection property, the first one is what we're using here. First sub toolbar, and it's contact, contact, right there, contact. Don't fool around with these things. So we have, this is the first one, contact. Another one for the second one. And please, when I say don't fool around with it, is that of course you're welcome to go look at the documentation, learn how to do it, and we're going to do some of those later on. But uh, yeah. So when I ran it without these connection and contact connection, it bombed out because it went through each other. Let's run it now. You'll see that there won't be an issue. And you can plot the change the scale here. Well, let's plot something and then reset the scale. Did it run? I think it did run. So let me try again because I'm not sure if it actually ran. Maybe I canceled it. Yeah, I think I canceled it because it was not letting me plot images. Right now it does. Okay. Okay. Reset the scale because you can't see anything here until you reset it, and then animate. That's the way it should be, isn't it? Isn't it? Anything that you don't want, you can hide. Let me, well, I'll leave it the way it is. So one Mesa stress right there. Change the rendering if you want. Material shading right there. You can see that. Now the force, if we calculate the force, we should be getting half of what we got before. Okay. So how do we do that? We go to the tree, right click, create resultant sensor, create reaction sensor. It says, where is it? It's that restraint that I use on the top, right? Or the bottom, actually, it really doesn't matter because it will be the same force. So it's this top one that I say, not the slider one, this bottom one, this one. Or you can use the clamp, it really doesn't matter. I'll use the one on the top that I said move up and update. I should get about 11,000. Hang in there. No. Okay. Remember, when we did the whole thing, we got 22,000. First of all, we were not worried about the validity, at least today. We're not worried about validity of these things. But 20,000 was, okay, was for both sides. Or 26,000, actually. It was 26,000, right? On both sides. On both sides, okay? And half of that 11,000, and half of that is roughly, I mean, we are not getting exactly half of it, but this requires, a more detailed study. What I'm saying, you see what happened, okay? You get almost half of what you got before. And there are other, reasons that they're different, not quite half, but anyway, without really doing a conversion study, mesh conversion study, this is all garbage. The first one that I did and this one, you really have to do a mesh sensitivity study in order to get to the bottom of things. I showed you the process. Please make sure you stay with the course. Don't wait for a week or 10 days trying to catch up in 3 nights in a row. It's not going to work.